So today I'm going to try and quickly review some things we did last time and then move on to how I think things work in 6 dimensions. So we saw that like 5D n equals 2 Yang-Mills can be described by looks like. So it has some twist given by maps from C2/2 cross R to BG. We saw also there's some kind of A twist, which turns us into C2/1 cross R to BG to RAM. We're counting some bundles. And in this picture, Z of a complex surface X is going to be the cohomology of instanton moduli space. And you should worry about compactifications there. That's some kind of B twist where these two odd directions are both thought of as differential forms. Or we get maps from R5 to BG, kind of like 5D analog of pure Chinese. And also there was a kind of a half twist where we use this the supercharge like epsilon 1 d by dz1. This gives us C1/1 cross R3 G. And here in this direction it's holomorphic. In this direction it's topological. OK, so I'm writing these down for you right now because what the plan is today, well, first I want to discuss how the 6-dimensional 2-0 theory is expected to reduce to these various twists. So the 2-0 theory in 6 dimensions has a twist which is topological in 4 directions, and again holomorphic in 2 directions. How do I know this? Proof, kind of linear algebra with the supersymmetry algebra. In this. This is some kind of totally trivial statement. That has, yes, exactly. OK, so what? So we consider this theory on R4 cross C. So we want to consider dimensional reductions of it to 5 dimensions, and then we will learn things about what this theory must look like. So first, what happens, the first thing we might consider is, let's consider it on R4 cross C star and reduce on a circle in the C star. Well, let's pause for a moment and think about what this must look like in 5 dimensions. So what does it mean it has a twist in these directions? I have a supercharged Q such that the image of Q is equal to 5-dimensional space of d dxi, I equals 1, 4, and d by dz bar. Okay. So I didn't spend much time in this earlier, but this is if you have some supercharge, how do you tell how topological or holomorphic it is? You compute its image in the space of translations, and any direction that is in the image of the supercharge is 0 in cohomology, therefore it's topological in that direction. But typically in Euclidean signature, the image will not be a real subspace. It'll be a subspace of the complexification. So we'll also get some kind of complex vectors. So anything like that means we have some it's holomorphic in that direction because d by dz bar is trivial. Now here we're reducing along a circle in the z direction. Well, this means that this supercharge will hit everything in 5 dimensions because it hits d by dz bar, and d by dz bar projects to something non-zero. It's not totally along this fiber. So it implies it'll be topological in 5D as d by dz bar projects to C star sake as 1 cross or. This is, I'll call this parameter or, to the vector d by d or, kind of radial vector, kind of under orthogonal projection. Okay, so we're only, wow. Okay, so here we got some twist of the 5D theory. What twist is it? So conjecture, this is the A twist. Actually, this is the only thing it can be. If you think about the supersymmetry, you find this is what it has to be. Okay, so this should imply that, for example, if X is a complex surface, and I consider the 2-0 theory on X cross C star, where it's topological here, holomorphic here, then the Hilbert space, the 2-0 theory on X cross a circle in the holomorphic direction should be the cohomology of Bunge of X. This is the kind of thing we might expect.
Is it clearly topological?
It's topological in the weak sense because it's cohomology. So if I vary the complex structure a little bit, it's not going to vary. So you really have to make care if you want to make it topological in the strong sense. I mean, diffeomorphism invariant. But it's, certainly if I take the correct compactification of Bunge, it should be deformation invariant. Will you ask the question? No? Okay.
But if I take something that's not in the different connected components.
Yeah, you might worry. I mean, but that's this kind of argument we have here is like just a weak form of topological. It says if I vary by some vector, it's 0. It doesn't say anything about global diffeomorphisms. Okay. Let's consider it on a kind of R3 cross S1 cross C. So we reduce along a topological circle. Topological circle. Then you might expect, well, the 5D theory must be mixed, topological and holomorphic. So there is only one twist. Twist like this, which is described by the one this kind of half twist we said a minute ago. C1/1. So one point to emphasize, reducing along topological directions is very nice. Because normally, if you were to do a dimensional reduction along some direction which is not topological, then as Andy has been emphasizing, it will kind of depend on the size of the circle. But here, because it's topological, really it's just independent of the size of the circle, and this is just exactly true. This should be kind of exact description of behavior of the 6U theory. Yeah. Not so much the choice of, well, you might be worried about the difference between compactification and dimensional reduction. I'm slightly worried about it too. But as we will see, this statement is actually, we can write down the 2-0 theory. I know it really well in the abelian case, and this statement is just true. The non-abelian case, don't understand it so well, but I have a proposal. So, third example. So, Witten, let's consider the theory on O3 cross S1 with a fibration by C, where the monodromy is going to be, well, we take this fibration to be a small bit away from the trivial fibration. So we'll take it to be something given by some vector field, say, the vector field. Allomorphic vector field. Then this should be, I'll explain why this one is particularly interesting in a second. So this should give us the deformation of the theory on R3 cross C1/1 to BG by the vector field V d by d epsilon on this space. Okay? I have no idea. This will turn out to be true. Well, why this example is important is that Witten considered the case when V is d by dz. V is equal to d by dz, sorry, z times d by dz. And then he says that in the 2-0 theory, we get Kavanagh homology. And so that in the 5D theory, we have the theory here now on R3 cross C1/1 with differential epsilon z. Sorry. Yes, epsilon z d by dz. I got it. I need to look at my notes. I think I made a. It's quadratic. It's not correct, right? So. I think it's if v is like some function times d by dz, then this will be f d by d epsilon with kind of with supercharge c d by d epsilon. Okay.
Just so I'm keeping track, if it were just d by d epsilon, that would give the Germain
Yes, exactly. If there would be a partial, it would be a mixture of, it would be kind of flat connections here, allomorphic things here, but we're counting them. Exactly, yes. But here, what does this look like? Like away from the z equals 0, it still looks like the RAM. So when z not equals 0, this is a topological. But in a way where we count things.
What does this expression mean?
Z d by the epsilon?
No, the statement where we count things.
Well, it means it's a theory like Roman-Witten theory or Donaldson theory, where the partition function is given by counting things. The Hilbert space is cohomology of some space. Local operators are cohomology of some space. OPEs are given by correspondence is acting in cohomology. It's a theory of the kind you love. The other kind of theory is like the B model, which is not like that at all. Or Chern-Simons theory is not like that either.
So I'm just going to ask, what does it mean when you say when z is not 0? Z is some sort of parameterized space, is that?
Well, like, I just on that open subset,
Oh, I see.
it looks like, and but at the origin it's going to behave differently. At z equals 0, so I mean clearly when z is not equal to 0, it's kind of homogeneous because I can rotate. It looks, but at z equals 0, there's some kind of defect, and on this defect lives Chern-Simons. Because it's a dimensional reduction. So he says we get Kavanagh homology.
So the Chern-Simons is those are fluid reduction?
Yes, exactly. On the orth 3. And this is true, at least in perturbation theory. I'll work this out, and it's kind of related to work I've done with John Francis. This is true in the sense that there are line operators which are supported at z equals 0 whose expectation value, whose correlation function's expectation value is the Chern-Simons knot invariance, or Schutz-Drive invariance. Okay. This is some kind of sanity check for the whole thing, right?
Do you want to explain what this theorem means?
Well, this whole thing is a factorization algebra.
This is a theorem about the 5D theory.
Yes, it's a theorem about the 5D theory, the factorization algebra of the 5D theory. Turns out away from, if I look at operators in perturbation theory, away from this z equals 0, there's nothing. That's because it's a theory where we count things. We're looking at homology of moduli spaces. In perturbation theory, we're looking at the homology of a point. But at z equals 0, there are some new operators that appear. So there's an E3 algebra of operators. This E3 algebra has the feature that its category of representations, which is in braided monoidal category, is representation of the quantum group. So as I said, this is related to work of myself and John Francis, who approached just Chern-Simons theory in that way. And we find, indeed, E3 algebra whose category of representations is that of the quantum group.
Sorry, I think I missed what the passage was to actually get to the to get to the Chern-Simons
variance. Maybe this, let's see, like from the E3 algebra or the,
I think that was the.
He was asking, the answer is you take back an expectation.
yes. Yeah, there are Wilson lines, which, this theory has a connection, like take Holland this connection along the 3-plane. But the theory is such that I can't move, if I move these lines in my 3-plane, it's all topological, but I can't really move them off. The Wilson lines don't survive.
I don't understand what's being asserted here. So I mean, to take this factorization homology, you need to know that this theory somehow is topological and that sufficiently extends sufficiently far down. So you can take factorization homology makes sense.
Oh, but I'm doing things more perturbatively than David was. So we get perturbative Chern-Simons invariance. So the quantum group near 1, when Q is near 1. And then, then everything is really determined by functions in E3 algebra as opposed to some higher category.
So this E3 algebra is a candidate for what I should be assigning to a point, at least, like, perturbatively.
Yes.
Cool.
Yeah, it's the local operators of the theory.
So can I extract the Jones polynomial out of this construction?
Yeah, in perturbation theory, in formal series when Q is e to the h bar. I mean, and really, this theorem is like not actually super hard once you know the analysis. Once you know that once you know that if you do perturbative Chern-Simons to the Chern-Simons action, you get the Jones polynomial. This theorem is not a hard consequence of that. Okay. So this was the first sanity check. So now,
This is a sanity check on Witten.
yes, well, I know Witten is sane, so maybe it's a sanity check on me that I'm like doing the correct thing with these 5D theories and. So I want to write down kind of a guess for what the 6D theory looks like. And it will satisfy my guess, because I really only know how to do things very well in perturbation theory, I don't understand the defect operators as well as I would like. My guess matches pretty well, but misses some things which come from like, where I put some singularities in the fields. Okay. Guess for zero theory.
This is going to be some kind of definization of the two theory where you forget some.
Yes, exactly. Yeah. Yeah, kind of poor man's version. Start with the abelian case. The fields should be the RAM complex of R4 tensor omega 1 star of C, i.e. locally constant maps from R4 to the space of holomorphic 1 forms. Let's see.
Choose zero theory means after the twist.
Yes, with this twist of. Yes, exactly, yeah. It's the full physical theory. I would be insane to claim I knew anything about it.
Sorry, what are the superscripts on the omega in that first?
Star, omega star, omega 1 star. So, well, remember I said at the beginning, to give a field theory, I need to give you some kind of sheaf of Poisson spaces with a non-degeneracy structure. Well, something that would assign to a compact manifold, a symplectics thing. Here, this is going to be a degenerate field theory. This will be a degenerate field theory. It has a Poisson structure. But it's not degenerate. So what's the Poisson tensor? So if I take the dual of this space, I find complex of order things on R4, tensor complex of order things on C, the shift of 5, sorry. The dual of 1 forms is 0 forms. So if I have these two elements here, alpha 1, alpha 2, in here, remember the Poisson tensor is a bivector. So it takes two elements of the dual and gives you a number. My Poisson tensor alpha 1, alpha 2 is just the integral of alpha 1 del alpha 2. Okay, so why is this a reasonable thing? So example, replace or 4 by, say, x, a complex surface, say K3 surface or something like that, then what we find, which is this is compact as well. Well, if we ignore the stuff coming from OR4, what I've written down is will be the Poisson structure describing the free boson. Find the free boson valued in the cohomology of X. The corresponding vertex algebra is equal to the one considered by Granovsky and Nakajima. Vertex algebra. Structure on the direct sum cohomologies of Hilbert schemes of n points on X.
So is this like a free chiral boson?
Yes, free chiral boson.
The assertion you're making here, and I would say it. The first assertion has nothing to do with Granovsky and Nakajima, and then you say, in fact, it's also equal to this thing, which is then supposed to match up with dimensional reduction of bundles.
Exactly. That's exactly right, yeah. So whatever we're saying, Z of this kind of abelian theory, abelian 2,0, on X cross S1 is indeed equal to the direct sum of the cohomologies of the Hilbert schemes of n points in X, and as we would expect. Further, if I take Z of this abelian theory on X cross an elliptic curve of modulus Q, this is equal to the sum Q to the n Euler characteristic of the Hilbert schemes and X, where this Q is the modular parameter. And again, this is a key feature of the 2,0 theory. When we reduce it on an elliptic curve, the modular parameter of the elliptic curve is related to the instanton number. And this guy is supposed to be the Vafa-Witten twist of n equals 4 in 40. So this is, again, kind of as we expect.
How does the theory know the compactification?
I have no clue. That's totally mysterious to me. But this is what, I mean, SMO appears everywhere in, for example, like Nekrasov's incidental counting work too, right? So I'm always really confused by that.
What calculation did you make here?
It was a Hilbert scheme rather than line numbers, right?
I made almost no calculations. I made,
I was going to say, presumably you calculated, thing you wrote down, you calculated something about Z at.
this theory is extremely simple. It's like a free theory, topological holomorphic. You can very easily calculate this partition function and its Hilbert space.
At what point exactly did Hilbert schemes enter? Did you look up the answer that Granovsky and Nakajima got for Hilbert schemes and noted that it matched the answer you got?
Yes.
By methods? Okay.
Yes, exactly, yeah. So this theory, I mean, it's certainly not obvious that this is related to Hilbert schemes.
Right, okay.
But it just so happens that it is.
But once you wrote down this theory, so you have some sort of essentially mathematical account of how this dimensional reduction works,
Yes.
and you just go back through whatever Vafa-Witten said and say all those same words about the mathematically rigorous.
Well, but there's still a theorem, right? In that it's going to be a non-obvious fact you need to know something about Hilbert schemes to say, look, if I just take this theory and I dimensionally reduce on my elliptic curve, I will get some Fourier theory, which is not obviously the same as the other Wald-Baffel-Witten down.
Can you say what that theory is? Or will you?
Well, it's that if I reduce on kind of R4 across an elliptic curve, we find a Fourier theory kind of maps from R4 to the space of closed one forms, homomorphic one forms. So the fields are like kind of Durham complex here, coupled to something from there.
Also, you have to know the statement that the elliptic genus is computed on that formula.
Yes. Yeah, exactly. The elliptic genus of this.
All right, so that's the elliptic genus of X.
Yes. Exactly. Yeah, so I take the elliptic genus of my theory X on a complex surface, like reduced on a complex surface to 2 dimensions. That is the Euler characteristic of the Hilbert schemes. I mean, this elliptic genus is very easy to compute because it's a free boson. Okay. So let's kind of guess for the non-abelian case. Non-abelian case. And the evidence for this is not nearly as nice for this one, but we can still use what people know in the physics literature to make a strong case. That the fields, okay, let's choose an SL2 triple, a principal SL2, given by E, F, H in our Lie algebra. In capital. So this implies a choice of decompositions of kind of negative nilpotent elements B minus, B plus, M plus subalgebras of G such that E is in N plus, F is in N minus. Okay. So this decomposition is just according to the weights of H. It's a principal SL2, so that's what we get this kind of thing. So the fields on or 4 cross C we can describe it as follows. Locally constant maps from R4 to there's 2 ways to say it which are equivalent. Opers on C, which is the same as G opers, yes. With this choice of principal SL2 and minus bundles plus a holomorphic connection, which looks like of the form E
Holomorphic connection on the G bundle.
on the G bundle, yes. On the G bundle of the form E times dz plus a B connection.
This is a holomorphic G bundle and minus bundle.
That's part of the structure, yes. But the connection does not preserve the n minus reduction.
But it sort of has this particular compatibility with the structure.
Yes, exactly. So we can describe this space. So for example, we can describe a DG Lie algebra describing kind of this formal deformations of opers. What is it? It's just omega 0 star C tensor n minus omega 1 star of C tensor B minus. The differential is this. Okay?
Is this a free field theory?
Oh, I haven't told you. It's not going to be free field theory yet, but I haven't told you the Poisson structure. Well,
I mean, the space of opers is just a vector space, right? So you're looking maps into a vector space.
yes, but it's going to have a Poisson structure which is not constant. So, not a. So what's the Poisson structure? Well, oh, actually, maybe just for a second, 0 and 1. So with the 4D field theory, as fields, omega star or 4 tensored with this thing. Okay, because it's locally constant maps from this to this.
So I'm used to spaces of bundles and spaces of bundles of connection and everything always having some gauge symmetries too.
Yeah. That's right. Well, in terms of the Lie algebra, the gauge symmetry is in degree 0, but in terms of the fields, this is in degree minus 1, this is in degree 0.
Oh, okay.
So the gauge symmetry is n minus gauge symmetry.
But these guys are rigid. They don't have it.
As David pointed, I mean, this complex is no. If you take the cohomology, there's nothing in degree 0 because bracketing with E is injective. But I like to write it this way anyway. I think it's. Okay, so what's the Poisson structure? Kind of the slick way of saying it, which Nick and I talked about some stage, kind of take a complex opers of sigma inside of log G of sigma is Lagrangian. And then a theorem of me and Nick Rosenblum is that Lagrangians inside ordinary symplectic things have a canonical kind of odd Poisson structure.
This is for sigma compact treatments of this.
Yes, but if sigma is non-compact, this thing will have a symplectic structure in the Verdier-Joule sense, and then the same argument will apply.
But it'll just be a map.
Pardon?
But it won't be a subset, it'll be a map.
It'll be mapped, but it'll have a Lagrangian structure.
Okay.
So you can model it as a sub DAGLA, whose complement is a Verdier-Joule, so it's really is Lagrangian. Kind of concretely, so I'll write down the Poisson structure ignoring the OR4, because this Poisson structure transgresses to the OR4. That's very easy. So I'll write down we will already see how to do that in the Abelian case. I'll write it down ignoring the OR4. The Joule of this C coefficient n minus.
So by transgresses, therefore, you just mean you add that extra thing from the dealing part? If
in the ideal case, you wrote down sort of a Poisson structure that only used the R4 part.
No, it used differential on the C part.
Oh, that was sorry.
Yeah. So we're just going to have something which doesn't involve any derivatives in the R4 part. We just wedge and integrate. C minus. What's the dual of this? Well, the dual of, I'll probably get the shifts wrong. Well, the dual of B minus is B plus, so the dual looks like, no, these shifts are right. Omega 1 star CB plus omega, so this is a 0, this is a 1 star Cn plus. Del plus E, del plus E. There's an extra term of the Dirac differential maps from here to here. So again, the Poisson structure has a constant coefficient part which is, if I take some kind of alpha in here, which is like the integral of alpha wedge del alpha, where alpha is in omega 0 star, C with coefficients in B plus. It's a compact support. But there's also a linear coefficient part. This is kind of a beautiful story. Basically, it's the failure of this thing to be a direct sum to be kind of the cotangent bundle of opers. Sorry, that's just, I don't have time to explain this point, but the story is very similar to the Lie algebra story. If I have a formal space which I represent as a DG Lie algebra, one of these Poisson structures on it is just the same thing as a Lie algebra structure. Now, we know that Lie algebra structures can be represented by Manin triples, which is a Lie algebra structure on the direct sum, Lie algebra structure on the direct sum of this guy and its dual. This is exactly what we have. This guy plus its dual is just local systems on C, which has its own DG Lie structure, and that's the one that gives us the Poisson structure. Okay.
Is this a way of saying critical simple reduction?
Probably, yeah. Like we're choosing some Lagrangian. Okay, so let's consider first a check of this.
Just for those of us who haven't been thinking about opers since we were doing, can you say which local systems are opers? I mean,
They're these ones. They're local systems. It's not.
like an SL2 local system, an SL2C local system on Sigma. C or
It's not a property. It's data.
so what is included?
So. Pardon?
You write opers is a subset of local systems.
Oh, on some. I'm kind of. If sigma is compact, it's really inclusion. If sigma is not compact, it's like a map with a Lagrangian structure. But an oper is, a G bundle with then. For simplicity, I'm trivializing the canonical bundle of C. If I wasn't trivializing the canonical bundle of C, it would be slightly more complicated. But in this case, on something with trivial canonical bundle, trivialized, an oper is a G bundle with an n minus reduction with a G connection, which is of the form bracketing with E plus something in B. So for SL2,
Yeah, I know.
yeah, I'm,
But is there some reason coming from the physics or from whatever that this should be the odd Poisson structure you put on it?
yes. We'll see this in a second. What's the check of this? So again, consider 2,0 on OR4 cross C. And let's replace, let's consider it instead an OR2 cross a cylinder cross C. So we reduce to 5D. To 5D along that circle. S1. So what do we find? I'll draw my cylinder. Here, we find some version of 5D Yang-Mills. And here, we find a boundary condition.
Is that a cylinder or a thimble?
Pardon?
Is that a cylinder? Looks, in your picture, it looks like a thimble.
It's a thimble. Yeah, I'm sorry. Physicists call it a cigar. I have no idea why. I can see what looks like a cigar, but you know. What's that?
I think that's what they call this car.
But you know, everybody else calls it, you know, a disc.
So it's a disc with a marked point at the
Cigars are diametric.
Yeah, but physicists often care about the metric.
Yeah, yeah.
But I don't know. I have a beef with this. I mean, there are almost no calculations in physics except for BPS stuff. Right? I know that's not quite fair. But with this 2-0 stuff, really, almost everything is a BPS stuff. For n equals 4 Yang-Mills, people have gone beyond that, and that's fantastic. Is that unfair?
I think it's slightly unfair. Wait, just literally, what does it mean that they're potentially reduced along this S1? Like the dictionary definition. What is it?
For me, the dictionary definition is I have a factorization algebra here, I push forward factorization, and push forward factorization algebras like you push forward sheaves.
So that this is totally okay, even though that is a singularity.
Yeah, you just push forward.
Kevin, I'm a bit confused by the data. Are you starting with just the 6D theory or 6D theory with one of its defects?
No, just the 60 theory, no defect. So when we reduce to 5D along this circle, we find a boundary condition. So, well, so as we've seen, so we're reducing along a topological circle. So this will be a boundary condition. Sorry, some more. A boundary condition for the mixed twist of 5D Yang-Mills, kind of which is on R3 cross C1/1 to BG. So we can view this theory as some kind of infinite-dimensional Rosansky-Witten theory. Of maps from R3 to RAM to Higgs bundles G and C. So this is not anything involved in compactification. It's just some kind of tautological homotensor junction. The fields in here are maps to some space of fields in here. So this boundary condition was computed by Gaudo and Witten in a slightly different language, but I'm pretty confident that this is what it is. I mean, they use like a very similar language, actually. They thought about Landau-Günzburg models with target Chern-Simons action function. So their claim is that this boundary condition is given by, comes from the Hitchin section inside of Higgs. Okay, so what we need to check is that if I take our 60 theory, so this is a picture of local operators of the 60 theory. Therefore, local operators in 6D are going to be kind of functions on maps from OR4 to RAM to the H intersection on C. Okay, and this is if you believe physics, this is really a proof because we really have lost absolutely nothing by reducing along a topological circle. So that's what did I say earlier? Here's something very ugly will appear. I said the local operators, well, a consequence would be functions on maps from OR4 to RAM to opers on C. Okay. Here's a very ugly fact that opers on C, this is isomorphic to the H intersection on C. It's not canonical, right? So, but I have to use it, otherwise things just don't match up. This is what I've been incredibly confused by for the last couple of weeks.
Is this somehow related to the choice of consonant or principal SL2?
It might be related to the principal SL2. I mean, you can turn, I mean, there's a kind of homotopy, or like this.
Choice of uniformization, I think. It's more than just homotopy.
It's more than, okay.
I mean, you can't do this holomorphically over homologized proofs.
Ah,
This is not holomorphic. This depends on data on the Riemann surface.
okay. Since I always work in perturbation theory, the simple thing I would say is that there's a homotopy between this guy, between del and 0, given by bracketing with f and d by dz. You know, the commutator of this with e is like del times h, and h is invertible in this stuff. So in perturbation theory, you really can do it.
So, is there any problem anywhere replacing C by just an arbitrary Riemann surface?
The problem would arise with what David said. Making this identification more globally would require more arbitros.
Opers are naturally a torsor for the H section, and that torsor is not trivial globally. If you take an oper, if you have Riemann surfaces that come with projected structure, you don't need a whole oper. You just need a Riemann surface. Over this space, Riemann surface with projected structures, you have an identification.
Okay. Oh, because you have a projector, because you have the SL2 in your group as well. So wait. Okay. Thank you. Okay. So why did we get the correct Poisson structure? Recall if we took the theory X on OR3 cross S1 cross C is supposed to be the 5D theory on OR3 cross C1/1, and S1 doing the S1 equivariant reduction. Oh man, I think I forgot to tell you this. This is an important point. At the beginning, we could reduce from 6D to 5D in various ways, and we find various different twists. One of the things we take this C to be fiber of the circle with some monodromy, or we do some different things. But one of the things I forgot to mention is we can also do an S1 equivariant reduction. And this deforms, this turns on this epsilon d by dz differential, which turns us to kind of OR5 to RAM. So once we do it S1 equivariantly, of course, what we expect to find is actually opers. Equivariantly, we find if I do the 60 theory on OR2 cross a disk cross C, we get a boundary condition for the 5D theory, which is maps, like, well, the 5D theory is maps from R3 to RAM, G local systems in R2, and the boundary condition is given by Opers on C. Okay.
So why not just say your theory is maps into the Hitchin section instead of into Opers in 6 dimensions, and then this would be a problem. I mean,
Because I also wanted to be a boundary, living on the boundary of a 7-dimensional topological field theory. And this Poisson structure I'm writing down is very natural to see in Opers, but it's kind of bizarre in the Hitchin section. Maybe that's the issue.
it's the same Hamiltonian reduction. I mean, it still has.
It still has the same Poisson structure. But the Poisson structure comes from the RAM differential. Right? I mean, there is, I mean, you could do it in the Hitchin section, true, and it would be kind of locally equivalent, and you would have a Poisson structure, but it would be a very strange Poisson structure, which involves the RAM differential mapping from the Cartan to the Cartan, and no other RAM differential. It just seems odd to me. See what I'm saying?
So a lot of these nice statements sort of feel to me like, I mean, at some point you write down various sort of topological theories that don't seem to depend on what dimension we're working in. Like at some point you write down a 4-dimensional topological theory, and it just seems like I could replace 4 by anything else.
Yes.
I guess the significance of the particular dimensions here is that we know some relationships to non-topological theories coming from these supersymmetries. And that's
Yes.
the only way we get to actually like know anything.
Yes, exactly, yes. So if you really want 2-0 theory, I can write down this formal thing involving Opers in any even dimension. But yeah, the 2-0 theory is in dimension 6, and I'm sure there's a good reason for that. Okay, so this, if you think about the kind of compatibility with the Poisson structure in this, the 5D equivariant theory, this kind of implies we have the correct Poisson structure in 4D, in 6D. So I don't want to get into this too much. The point is, if we take the 6D theory and just reduce it on the disk, because we have these extra 2 topological directions, the Poisson structure, we don't really see it unless we make things equivariant. This is like the points that Tudor was making. When we make things equivariant, we more quantum. So by making things equivariant, we should see the correct Poisson structure, and we do, because it's on the back. OK. I'll give you one more check. So Chris Beam and Leonardo Rastelli computed and kind of equivariant version of the 2-0 theory. Kind of on R4 cross C and equivariant on R4 with respect to 2 rotations. And what they found is just like a vertex algebra at the fixed points. Algebra on C. In a similar way we did for Chern-Simons, by making it, as Tudor said, by making it equivariant, we can move off the C. They didn't use this language, and there's something to check to show that the way they describe it in terms of superconformal symmetry is equivalent to this way I want to describe it. And that this vertex algebra is a W algebra.
So that is also when it's like 0 everywhere else. Like
Exactly. There are no local operators except on this curve. So in our story, if I take this thing on R4 tensor this kind of Opers thing, if we do it equivariantly on R4, then of course we find Opers. We find just kind of Opers on C. On C, which when we quantize, we find the W algebra. Point is that the Poisson structure we're using is the one which quantizes at the W object. How am I doing for time?
You're almost done.
2 minutes?
Yeah.
Okay.
Plus episode. Whatever.
Okay, so what?
Very important, son.
What was that?
So say something important sounding.
Yes. Okay, so maybe just a few more comments about this story. So, as I said, at the beginning, there's something missing from this story, in that we don't immediately find all the operators we would expect in the 5D theory once we reduce something in a circle. So let me explain a bit about this. So suppose we take our model for a 60 theory on kind of OR4 cross C, and suppose we naively reduce to 5D along a topological S1 by taking Hotchkiss homology of local operators. So this kind of reduction will pick up all the operators in our theory that are built as functions of the fields, but it will miss those operators which arise by prescribing singularities. Then we find what we find. Let me just write it very, very quickly and very heuristically. Pardon?
Oh, I was just asking if this one naivety was the same as the usual prescription for dimensional reduction of the factorization.
Yes, it is, exactly. It is that. But like the point is, this factorization algorithms miss something in the way I know how to construct them. Well, what do we find? We find omega star or 3 tensor this kind of Opersy thing. Let's just do the abelian case, because the notation is simpler, but it works in general. We find omega 1 star C, and then a tensor where epsilon is equal to the class in H1 of the circle. So I'm making this in degree -1, this in degree 0, just by some conventional shift. So you want to compare this to the 5D theory directly. This will look like omega star of OR3. What do we find here? We find the Lie algebra controlling deformations of Higgs bundles. 0, -1, omega 0 star C. So I write the other one here too. C into V0. So we find that there's a map at the level of fields. There's a map taking the Ram differential. Find a map at the level of fields. And so a map from Hotchkiss homology of the 60 theory operators to the 5D theory operators, which has all of the features we said it should have. It takes, equivariance to one twist. It takes, it takes this kind of omega background thing to the different twist, exactly as we should set. Respecting supersymmetry, as I said. Pardon? I wasn't here on the first day, unfortunately, but probably, right?
Sorry, which one?
So Pia was asking if this map I'm writing down is the same as the map you wrote on the first day.
This is something that local operators from the 60 theory, not the local operators from the 5.
Yes, that's this piece here. Local operators map to local operators. But there are some local operators in the 5U theory you don't capture as local operators in the 60 theory. And they should come from kind of Hochschild integrals around the circle. That's right. And okay, the reason, so maybe I'll end there. We've constructed some kind of toy model for the 60 theory, which has everything we want. We reduce it along a circle. We find a map to the 5U theory. The problem is this map is not quite an isomorphism. Just because, while I've written it down in the abelian case, it generalizes for formal reasons for the non-abelian case. This map is not an isomorphism just because I miss the kernel of d by dz. So if I care about the kind of holomorphic structure, I find everything except for some kind of finite number of operators. So it's close to being an isomorphism. But for the twists that will give you Chern-Simons theory, you miss exactly the thing you need. So I don't know how to categorize Chern-Simons theory from this. OK, so I'll stop there.
I didn't understand something that maybe you explained more than once. So earlier in this talk, you had some dimensional reduction, some theory to something which includes bundles on output.
Yes.
And then later, you defined the 60 theory.
Yes.
And you made some dimensional reduction to something which should be the same thing and appears numerically to be the same thing in the abelian case.
Yes.
But there was presumably some physical argument explaining why you should see those bundles on the surface as that reduction. What happens if you run that argument in your theory?
Yes, I think it won't quite work for the same reason this kind of thing, some kind of failing here. And maybe just to be precise, like we're never going to get anything involving bundles on an arbitrary surface since it's something so simple. You only have hope to find something like this for bundles on C2 equivariantly, or maybe bundles on a K3. Just
What's the difference? Bundles on C2 equivariantly somehow something.
but you take a random complex surface. I mean, Donaldson theory is insane on that. You're never going to. It's just too complicated, right? There's no good. You don't think? I mean, you're the expert in this, so I'm.
I'm not any sort of expert. Any integral you want to make having bundles, that's the abelian case.
Mm-hmm.
Anything you want to compute, equivariant theory on C2 already knows it.
But it's certainly in the abelian case.
Yeah. So in the abelian case.
On the abelian case, it's all fine. Yeah.
But I mean, you were explaining that. How to say? You were saying that you didn't know how to see the Hilbert scheme.
No, I don't know how to see the Hilbert scheme itself. I know how to see its cohomology.
But there was some argument. So the question was, there was some argument in the original physics which explained why you should see bundles.
I think here so the argument there was you reduce the 60 theory along a torus, you get certain twists of n equals 4 theory. So what I found in this model, if you reduce the 60 theory along torus, you do find something with kind of the right amount of supersymmetry to be that twist of n equals 4 theory.
Okay.
But it is not the same in any obvious way. So this is a point maybe where it differs in physics. I've maybe a different duality frame or something.
Okay. Great. Maybe we can continue this conversation over lunch or afterwards.